Hi, my name's Rob. I'll be giving a presentation on rehabilitation strategies for a section of the Forelli Highway as part of my major assignment for the CPEE pavement rehabilitation course. So we've got a fair bit to cover as part of this presentation, so I'll give a brief overview first, outlining some of the key focus points we intend to touch on throughout. Initially, we'll have a bit of a look at the project objective and then move on to the available site information and undertake some interrogation of that data that we've been provided with. And we'll also outline some further investigations, as there is some gaps with the data, so that'll be part of the recommendation for further information gathering. However, we'll use the core information we have to identify the core issues throughout the site to help us target our treatments and focus them in the correct areas. And this will primarily be split between addressing roughness and structural aspects. And once we've identified these, we'll have a look at what treatment options will be viable and formulate two overall strategies for the site. And then we'll lastly end with a bit of a recommendation and closing summary. Having a look at the project site itself, it's considered to be a 4-lane highway located in Western Victoria, with the west and eastbound carriageways being physically separated, with the focus of this project being on the westbound carriageway. And it's also assumed to be of a moderate traffic volume and located in a semi-rural environment. Concerning the project objective, the site is targeting a 20-year design life, of which we've been provided with the design traffic loading to achieve this, and it differs slightly between the inner and outer lanes. And we've also been provided some condition data for the site to evaluate and govern the treatment selection going forward. Namely, this is the roughness, deflection and curvature, which we'll touch on shortly in more detail. However, the primary aim is to develop 2 rehabilitation strategies for the site, which focus on the factors listed below here. The first one being economics, so those upfront treatment costs, the maintenance costs, and how these will equate to a whole of life costing over the 20-year period for the treatment selected. We've also got the impact on environment, so that could involve the use of heavy virgin materials, so new materials, or if it's the treatment allows for good recycling aspects, such as in situ stabilisation or something similar. And then lastly, we've got the road user impacts. So these may relate to level of service, with the condition and ride quality of the road, but then also construction impacts that may cause delays or congestion. We've also been provided some general site information. So we can see on the left here we've got a bit of a feature survey, and that really just covers streets that intersect throughout the site, as well as a couple of seal changes down towards the end of the site, and the site also ending on abutting Saltwater Creek where the bridge is located. So there's a few important key things that drop out from the information provided. We know that we've got 3.5 metre lanes with a metre sealed shoulders on either side of the 2 lanes. The site's also approximately 3.5 k's in length, and we've got the option of raising the site by 150mm for the majority, but as we're getting close to the bridge, we've got to try and maintain the existing surface levels to tie into the abutment appropriately. The other bit of crucial information we've been given for the site is the existing pavement composition, which we can see the pavement's primarily granular based, but it does have a fairly thick asphalt with a 50mm asphalt wearing course and then a 75mm levelling course as well. And plotting the structure of this on the left really shows how much pavement we've got there existing, which sums up to about 800mm cover over the existing subgrade. Since we've been given the design traffic loading for the site, taking the larger design loading and having a bit of a look at what a conventional granular pavement design would require in terms of minimum cover over the subgrade, we can see that only 370mm of material is required compared to the 800mm we currently have, indicating that there's not really a lack of cover issue present throughout the site. Just keeping that in mind when we start to have a look at some of the distress modes for the other condition data. The first bit of condition data we're going to be having a look at is the roughness for the site. So this is interpreted as IRI, which just stands for International Roughness Index. And to break this down into simple terms, it's basically how rough the pavement rides as you're driving across it. So we can see the data looks fairly consistent for both the inner and outer lanes, and initially sort of averaging around 3.6, 3.7 through till it comes to a larger spike at around chainage 1.2 to 1.4, then lowering back down to an average around 3.5 consistently until we start approaching the bridge, where we see some significant increases through to the abutment. So overall, the site is considered to have probably a moderate level of roughness with a few areas of higher roughness. So the next bit of condition data we're going to have a look at is deflection data, and this gives us a bit of indication of how the pavement's structurally performing through how much it deflects during the test. So we can see again at the inner and outer wheel pass as well as the outer lane and inner lanes follow similar trends overall. But the first thing we'll notice is where we had that high roughness spike at chainage 1.2 and to 1.4, we don't really have high deflection figures, so that sort of indicates that the pavement may have been patched and there may have been some maintenance occurring, which is sort of relevant through the whole site where we've got that variation in the deflection and roughness data. However, we can see on approach to the bridge again, we start to get really high deflections, which corresponded with the high roughness figures we've got, indicating there are some structural issues approaching the bridge. The last bit of condition information we've been given is curvature data, and this gives us a bit of an indication on the stiffness of the pavement. And we can see it following a similar but probably more pronounced trend compared to the deflection data. But then we've also got that sharp rise on the approach to the bridge where both deflection and roughness were also ramping up. So while we have been given some good detailed condition information, there are some gaps that probably don't allow us to fully pinpoint the exact distress issues throughout the pavement. So we've just outlined here a few recommendations of additional information that would be good to be included. So particularly some further investigations where the pavement distress issues seem to be higher towards the bridge section. Some also detailed test pit log information, and this would also include potential moisture content and in situ CBRs, particularly for that section on approaching the bridge. There are also a few high variance items within the data set we were provided with. So we've only been provided with 100 metre level data, which has already been summarised up. So it'd be good to get the full list of data and be able to interrogate down to that detailed, potentially 10 metre level. And the last useful bit of information would be a visual survey that's chainage referenced. So this would allow us to line up potential maintenance patching with those areas we saw before where we were getting a high roughness but low deflections. So initially, following the review of the condition data, we broke the site up into lots. And this was primarily based on where we saw similar distress issues. There was one overriding one for the site where obviously everything started ramping up towards the bridge section, which in this case we've called Lot 5, whereas for the remaining length of the site it was fairly uniform with some minor variations. However, with the curvature data that was a little bit more pronounced, so we've broken it up into lots primarily based on that, with the thought that that treatment for the initial 3Ks of the site is going to be primarily focused on roughness. The curvature may help us to optimise some of those surface treatments. So we did a bit of a check to confirm whether or not there were structural issues present within the pavement, and that was by checking the characteristic deflection against the designed deflection that we'd calculated for each of the lots. And this sort of just reinforced what we'd seen earlier based on the condition data, that lots 1 to 4 fell below the design deflection, indicating that they won't need any structural rehabilitation to achieve the design period. Whereas this wasn't the case for Lot 5, with its characteristic deflection sitting beyond the design deflection, indicating it would require structural treatment to achieve the 20-year design life. So based on this, we broke the treatments up into 2 main streams. So for Lot 1 to 4, looking at treatments that prioritised addressing roughness for the site, so we could achieve an adequate roughness for the 20-year design period. Whereas for Lot 5, targeting structural rehabilitation options to ensure it meets that 20-year design life. Concerning treating the roughness, we looked at 4 options, so those being a granular overlay, an asphalt overlay, an asphalt inlay, and the last option being a targeted approach to roughness initially and followed by an overlay later at some stage. So we'll give a bit of a rundown on those four options over the next few slides and then end with a bit of a evaluation and summary of our two preferred ones that would go towards the development of the rehabilitation treatment strategy. The first option is a granular overlay. So the thought with this one is that we'd have to mill out 50 mil of the existing wearing course and then place 100 mil granular material on top of this. The reason for milling it out is to get a more level base given the moderate to high roughness throughout the site, as well as allow a bit more tie-in of the gravel. It has a few minor positives. It allows us to probably reuse some of the asphalt in the wearing course, but only a small portion. It also might end up exceeding the pavement life given the additional 100 mil structure adding to the already quite significant pavement structure. But it does come with a fair few issues, I suppose, with the main one being we're leaving a 75 mil asphalt layer within the pavement, which may cause some issues down the track. It's also probably one of the slower construction options for addressing roughness, as well as we end up with a bit of a higher drop off, and it's also quite an expensive option compared to the asphalt alternatives. Next up, we've got an asphalt overlay option. So this leaves the existing pavement intact and just aims to go straight over the top. So we'd apply a correction course initially, approximately 40 mil, just to take out as much of the roughness as we can, then proceed with the final wearing course. And we've got a slight difference in thickness between some of the lots 1 to 4, and that's just because some of the detailed fatigue checks we've undertaken. So this option definitely has a few advantages. It's probably one of the quickest options, also relatively cheap. It doesn't excavate any of the existing materials, however it will require a lot of new asphalt materials to be brought to site. And it does also cause the pavement to raise up slightly, not as much as the granular overlay option, but there's still going to be need for some correction due to the drop off. An asphalt inlay option, so this looks at milling off some of the existing surface and then coming over with a similar overlay treatment. Probably the main advantage with this one is it allows us to use some of the existing asphalt material, and it also reduces the extent of the pavement drop-off issue. But it comes at a generally higher cost than the overlay option, as well as being a bit slower due to the additional milling process that's involved. The last treatment option we've got towards dealing with roughness is a bit of a different approach, so it's more of a staged treatment. So initially we're just looking at targeting those high roughness areas and addressing them up front, and then following on in say 5 years time with an asphalt overlay. So we've shown here on the roughness plot below a bit of a potential intervention level that we might use, that being 3.8. So we target anything over that intervention level to be dealt with in year 1, and that would allow us to get the site back to probably an acceptable level of service, and then follow up with the standard sort of asphalt overlay in that 5 years time. And this has some advantages. It's relatively quick, like the standard overlay option, and it's also the cheapest one because it optimises, I guess, targeting the roughness rather than a full correction course being running through the site. However, it does still, like the overlay option, have that slight issue with increased drop-off height, and there also might be some risk to the pavement if we delay the resurfacing for so long, so that would have to be carefully managed. So here we've got a bit of a summary of the costs for the 4 options, where we can see the targeted approach has the best whole of life costing, whereas the granular overlay has a significantly higher cost, around 50% more than any of the other asphalt-based options. And based on that, the granular overlay is not considered a viable treatment for the site. An asphalt inlay cost is also slightly higher than the 2 overlay options, and it doesn't seem to provide the additional benefit to justify that additional cost, so that's considered not a preferred solution as well, leaving the 2 asphalt overlay options to form part of the 2 treatment strategies going forward to deal with the roughness portion of the site. Next up, we're looking at pavement structural treatments. This is specifically for lot 5. So I'll be looking at 4 options as part of this, with the first one being a traditional granular pavement with thin asphalt surfacing. Next one looking at a granular and asphalt combination. A cement stabilised option, and then a more probably unconventional option of implementing some drainage improvements first, monitoring, assuming there's going to be some improvement, then lessening the extent of pavement works. However, in all cases, we're assuming to address the pavement deficiency, we need to rehabilitate right through to the sub-base layer, and this will be applied consistently across all the treatment options so we get a reasonably fair evaluation, obviously apart from the fourth option where we're looking at improvement occurring through the drainage improvements. And similarly to the roughness evaluation, we'll have a look at which two treatments stand out and will form part of the two rehabilitation strategies going forward. First up, we've got the granular pavement with thin asphalt surfacing. So this would involve fairly substantial granular layer being constructed. As we can see here, it involves three separate granular layers, and then a 10mm waterproofing seal followed by 40mm asphalting. Now this option would make good use of the existing extended granular material, provided it can be reused, and it also comes across as the cheapest cost option. However, it's likely going to be slowed by the multiple granular layers required and the necessary dryback that would have to be achieved, as well as the pavement itself being probably more susceptible to moisture ingress, which is likely the primary issue that needs to be addressed. Next up, we've got the thick asphalt and granular pavement. This is similar to the prior granular pavement. However, it differs in that the base layer is now substituted as an asphalt base layer. And then we've got the 40mm wearing course atop this as well. This one would have some reuse potential, as it could reuse some of the existing asphalt and granular material as part of the pavement construction. And the thick asphalt would provide a good base rut resistant layer, potentially of very low maintenance. However, it comes in as the most expensive treatment option out of the four, and also requires a larger quantity of new material to be mobilised through the site, mainly due to the additional asphalt being used. Moving on, we've got our cement stabilised pavement, so we've gone for a more heavily bound stabilised option of 5000 MPa here, and this would involve two layers of stabilisation coming to a total of 375 mil, and atop this we would have a 135 mil base course followed by a waterproofing seal and wearing course of 40 mil asphalt. So this option probably has the best reuse of existing materials, given it can stabilise in situ for the initial stabilisation layer and then reuse a lot for the follow-up one. It also likely provides the best moisture resistance for the pavement structure. However, it does have some negatives against it. It requires a lot more different construction processes, as you're involving stabilisation as well as granular and asphalt wearing courses, and it's also a moderately expensive option. The last structural option we've got is a bit of an unconventional one, so it's looking at implementing some drainage improvements up front in year one and then monitoring that for a 12-month period. So these would be upgrading the table drains and putting in some cut-off drains, as well as some moisture protection to try and reduce any ingress from the creek into the pavement. And it's based on assuming that this would have an effect that improves the strength of the lower pavement layers, such that the treatment can be more isolated to the base layer rather than the sub-base layer. So this would result in a 250mm in situ stabilisation, but only a lightly bound 2000 MPa one, with a 10mm waterproofing seal and 40mm asphalt wearing course placed atop this. So this has particularly good reuse of the existing material, and then also with the drainage works it specifically targets the likely cause for the distress. However, there's some risk as it doesn't fully renew the entirety of the pavement structure, and the fact that this is the worst section of the site and it would have to be delayed for a period while the monitoring of the drainage effectiveness is undertaken. So here we've got a bit of a summary of the costs associated with the structural treatment options. We can straight away see that the thick asphalt granular option is significantly higher than the other three options and compared to whole of life costing. And given the benefits were fairly minimal, this one's ruled out as a viable option. We can see that the granular sort of standard conventional pavement has the best whole of life costing, but this is, I guess, undertaking a heavy assumption that it's going to be able to achieve that target design life and not suffer from the distress issues that the current granular pavement is suffering from, particularly given the other two options both have elements that either increase the pavement's resistance to moisture or specifically target improving the drainage of the site, making these two, even though they've got a slightly more higher cost, they're probably preferential treatments as opposed to the standard granular pavement, with these two being selected going forward for the rehabilitation options. So here we've got a bit of a summary of the two selected rehabilitation strategies for the site based on the review we've conducted for the various treatment options. So for the first strategy, we've got an asphalt overlay treating the roughness for lots 1 to 4, and this is followed by a cement stabilised option to treat the pavement distress of lot 5. And for the second strategy, we've got a targeted approach to deal with the roughness for lots 1 to 4, so initially treating those high areas and then coming back in, say, 5 years' time to do the full overlay at a later date. And then concerning lot 5, we're doing a targeted approach to drainage and monitoring and hoping for some improvement, and that way lessening the depth of the treatment and isolating it to the base layer to improve the ride quality and structural strength of the base layer rather than the full depth pavement. So both of these are fairly different in their approach, with strategy 1, I guess, erring on the side of caution, where it's coming in as a bit more of a cost, but there's a bit more guarantee that they're going to address those issues immediately. Whereas the second strategy tries to be a bit more innovative about how it approaches it, and it manages to achieve a bit of a cost saving if it is successful, but there is a bit more of a risk associated with taking that option. Ultimately, the recommendation would be for strategy 1, just erring on the side of caution. While it does come in at approximately 110,000 more in terms of whole of life costs, it has substantially less risk in comparison, and it also addresses the site immediately up front, and you're not having to remobilise to the site multiple times over the initial year periods. And it's also likely, given the extent of stabilisation and cover obtained, that you're going to gain beyond the design life of the pavement as well. So there'll be some potential residual value left in that. But it would really come down to if we were truly able to pinpoint with that additional, I guess, condition information sort of discussed earlier, refine addressing that core issue, then strategy 2 may become a more viable option for the site. And lastly, just want to thank you for listening to the presentation. I've no doubt probably gone over the allotted time, but there was a fair bit of information to cover, so thanks again.